First of all, I must thank the organizing committee for giving me this lecture here. And I must also thank Torin Barry for giving me this chance. Today I'm going to talk about the cohomology algebra of polyhedral product spaces. And since the cohomology algebra is the diagonal tensor product of two algebras, we have to see the definition of diagonal tensor product. A diagonal tensor product are defined on graded groups, that is the direct sum of subgroups for A and B. Here the lambda is the index set. It is very important because only when the direct sum with the same index set can we define their diagonal tensor product. So for such two groups, graded groups, the star means graded groups because we are all taking cohomology groups. The star means nothing, just to show that it's a graded group of cohomology groups. So for such two direct sum of groups, we define their diagonal tensor product to be this group. It's this is the group definition. Later we'll talk about the algebra structure if A and B are both algebras. Now, the next is to compare the usual tensor product of the two groups, graded groups. The usual tensor product is also a direct sum because each of them is a direct sum of subgroups. So the tensor product is the direct sum group of this. The index set is lambda times lambda. Alpha beta in lambda means the index set is lambda times lambda. And so the diagonal tensor product, the index set, is in fact the diagonal of this lambda times lambda. So it is called diagonal tensor product. And our computation is that the cohomology of the polyhedral product, first the group, is a diagonal tensor group. Let's see. First the definition of polyhedral product space. This is already defined by Tony in his lecture, and I think many of you are more familiar with it than me, because I'm not a chart topologist. So it is thus defined. I think you're familiar with it. Then we'll see our theorem is that let Kxa be a polyhedral product space. Our condition is that this is the homomorphism of cohomology group induced by the inclusion map, and everything is over a fixed ring F. Here we require F to be a fixed ring. Everything is over it. So is a module over it. So the condition is that the kernel, co-kernel, and image are both free modules over F. This is our condition. This seems a very strong condition, but in fact not. Many important cases, such conditions are satisfied. For example, if F is a field, it's always satisfied. So with this condition, we have that the cohomology group, here we're not talking about the algebra structure. The group is the diagonal tensor product of first group, the second group. What are the two groups? The first group is called the total cohomology of K. K is a simplicial complex with vertex set of subset of M. Though M is the set from 1 to M, and M integers. And we'll see the definition later. And the next is another cohomology of the sequence of space pairs, Xa underline. That is another cohomology. These groups are all direct sum of its subgroups. And this polyhedral product, the cohomology here is the group, is the diagonal tensor of the two groups. And this result is obtained by Barry, Bandowski, Cohn, particularly in their famous paper very long ago. I mean the group structure. They get the result from the geometrical stable splitting of the space, geometrically from this space, ZKXA, polyhedral product space. But in fact, from this result is that we explain that group or describe that group from the point of view of diagonal tensor product. And our computation is for purely algebraic. In fact, we first want to use the mere V-spectral sequence to compute the cohomology. And in fact, we prove homology, everything. You see, this is a condition that makes everything dual, completely dual. So we always compute the homology case and use the Meyer-Vitro spectral sequence. And to prove the spectral sequence collapse, we find an algebraic model that directly computes its homology. So the spectral sequence was thrown away. And let's see the definition of these two groups. This H star K and H star XA. The index set, as you see, the diagonal tensor product is always defined with an index set, that is the direct sum of its subgroups. So the index set is this. M is the set of m integers from 1 to m, and any two subset disjoint is this set. All such set form an index set. It is just a set for indexed epsilon m. The total cohomology group of K over F is this. It is the direct sum, of course, of its subgroups. This subgroup, H sigma omega K, is defined in this way. It is the simplicial cohomology group. -1 means degree uplifted by 1, and this is a simplicial complex. This K sigma omega is a simplicial complex that is the sigma link, the link of sigma, restriction on the omega. And its set is all those subset of M, tau. Tau is a subset of omega, and their union is a simplex of K, and their union is they're disjoint. So this is the case when sigma is a simplex of K. We define this. And when sigma is not a simplex of K, this we define it to be the void simplicial complex. Notice that this is a simplicial complex without even the empty set. We have to use this here. And this make all the conclusions very complete categorically. So notice the difference. This usually we have another simplicial complex with empty set that has an empty simplex, but this simplex has no simplex at all. So that if we take this, if K sigma omega equals the void simplicial complex, this is 0. And if it is the empty simplicial complex, this is not. This is F. So this is the difference. We have to use the definition, use this simplicial complex here. This is the total cohomology group of the simplicial complex K. And in fact, this, let's see the next. This is easy. This group, the cohomology group of this sequence of C-double complex pairs, XA underline, that is that's defined. It's a direct sum of groups. Each of this is defined in this way. H1 tensor with HM. Here the tensor is not, we don't have any index set, so it is the usual tensor product. And each subgroup is defined in this way. Its construction a little bit similar to the construction of polyhedral product space. In fact, in our proof, many things were constructed in similar way. This group, what I want to say is that this group seems a very complicated group. No, it's not. It's in fact a strict tensor product of subgroups. We'll talk about it later. It has two, in fact, there are two ways to describe this group. This H epsilon here is from the point of view of direct sum. If we have another point, we take the direct sum of three groups. We get HK. Not this. Suppose it is. I'll show you this. If we define, for example, we find this equals kernel. I write the homology case, co-kernel. If we define this group, then this group, of course, here is the dual case. We'll show the since everything is due, it's the same. From this point of view, we have a description. From another point of view, it is this H1 tensor. This is a very important structure. It is both a direct sum of subgroups, and from another point of view, it is a direct product, tensor product of groups. We'll see its structure later. So as we see, having defined these two groups, we have this conclusion that the cohomology group, in fact, I only write the cohomology case. The homology case is the same, has the same form. The cohomology group of the polyhedral product space is the diagonal tensor group of this total cohomology group of K and the homology of XA underlying. And so now we have determined the group structure. What about the algebra structure? It's very natural it's very natural. You may see that if we can if this has an algebra structure, and this group also has an algebra structure. Suppose they have their own algebra structure, then we have a very natural definition of diagonal tensor product of algebras. If we could define this, then is this cohomology algebra isomorphic to the diagonal tensor product of these two algebras? This is true. And so the most important thing is that we have to define the algebra structure of this group and this group. We have to define this. Since we have to settle this, this is quite a general case. What I want to say is that this condition is not very strict. So this is quite a general case. In this general case, the two algebras none of them are associative algebras, and their diagonal tensor product is an associative algebra. This is very interesting because diagonal tensor product behaves very different from the usual tensor product. These two algebras, none of them is in general associative, but their diagonal tensor product is associative. So we have to see the definition of diagonal tensor product of algebras. Here we want to stress that an algebra means just a graded group with a product that may not be associative. We don't need it to be require it to be associative. And suppose if an algebra is the direct product of subgroups, then we first see that when the algebra has such a direct sum structure, its product, this pi, is uniquely determined by its restriction product. That is, this is very naturally defined because every beta gamma is a subgroup of this. It's a summand group, and I is the injection. This is the product, and this is the projection to its summand, A, I, alpha A, and this determines restriction product. From this point of view, it's very easy to describe some algebras. And so, as we see, if an algebra is the direct sum of groups, then its product pi is uniquely determined by we call all such. These alpha beta gamma is taken over any lambda, any elements of lambda. So it's determined by all its restriction product. So the definition is very natural. In fact, from the point of view of product of elements, we see that pi bc, if B in this summand group, C in this summand group, then their product is the sum of this direct restriction product with alpha taken over lambda. It's very natural. This idea is very natural. And now let's see the diagonal tensor product of two algebras. So for two algebras, A, that is the, oh sorry, this should be, I forgot, there should be a star here. It's nothing, I left the star. For two algebras, that is the direct sum of groups, then we define their diagonal tensor product. The group is the usual diagonal tensor of groups. The product is, of course, should be a little different. For A, this, B, this. Their diagonal tensor product is this. Here I want to stress it's in fact it looks a little bit complicated. In fact, it's very easy. Let's see the usual tensor product of these two elements. It's just that this index set alpha, the first alpha and the second alpha are different. That is the usual tensor product of algebras. But here we require their index set to be the same. This is the diagonal tensor product. This definition is also very natural. And from the point of view of diagonal tensor of restriction product, every restriction product of this diagonal tensor product is the tensor product of their summed restriction product. So this definition is not very difficult. It's easy. And so another thing is that you see for a given algebra, many of its restriction product is 0. So the more 0 restriction products are, the algebra is simpler. And the diagonal tensor means it should be the simplest, because any one of the two is 0, its total is 0. So diagonal tensor product, in fact, the two algebras that are complicated algebras, their diagonal tensor product may be simple, because any of the two is 0. This is 0. So diagonal tensor product is, from this point of view, is the most possible simple algebra constructed from the diagonal tensor product of groups. And this is our result. Conditions are the same as before. Just the polynomial such that the three kernel, co-kernel image groups are all free groups. Then this cohomology algebra of the polyhedral product space is this is an algebra and this is an algebra. This algebra structure, this product is called the universal product of the total group K. And this product is the is the product of this XA underline. So we have to know the definition of the product structure of these two algebras. The universal cohomology algebra of K is defined as follows. This is a little bit complicated because we constructed from this algebra structure is obtained from an algebraic approximation chain complex, which is it makes this definition. So it looks a little bit complicated. We can only define the simple. The only way to describe its product structure is to define its restriction product. Its restriction product is induced by this simplicial chain complex. I forgot there should be a sigma, degree uplifted by 1. Sorry, this should be degree uplifted by 1, and this is induced by, this is defined as follows. A little bit complicated. First, if the index set doesn't satisfy this conclusion, the product is 0, and the otherwise, it is in fact the union of the two simplex. If their intersection is not empty, this is 0. And there's another with omega prime, another condition. And otherwise, this K1 to Ku is just the union. And we require everything to be in order. Suppose the vertex set is given an order. And so there is a sign in this, is the permutation sign. And the cohomology algebra of this is, as I said, this group, this H epsilon X1A1 is just similar to this. The kernel, co-kernel image direct sum added. And this group, the algebra product is defined as follows, which here, product xk means the cut product of this xk, this space. And this cut product, this product ak, pi ak, means the product of this cut product of ak, this space. And given this, this is also comes from an approximation complex. So it's thus defined. What I want to say is that these two algebras are in general not associative. This algebra, universal cohomology algebra, is not associative in general, and this is always not associative. And this.
Could I just clarify something? Could you go back to where you got the tensor product?
Where?
There. Sorry. Where you have the cohomology of the polyhedral product equals a tensor product. That's it, there. Okay. Now, I just want to try to understand this complicated product. Basically, if I take a class in the left and a class in the right, two classes, and I want to multiply them together, right? I'm going to multiply the something tensor something with something else. The target of the product, can change the combinatoric part, so that when you multiply two things, where they end up can be complicated on the left-hand side, and your definitions are meant to encode that thing. You can't. What I'm trying to say is, you don't take a class tensor a class and multiply it by another class tensor a class, right? And just multiply on the left and multiply on the right. That's what I'm trying to say. It's not as simple as that. Is that correct?
You mean my sign is not correct?
No.
Your English is a little bit too hard for me.
Okay, let's talk.
I'm very sorry.
It's okay, sorry.
And so this is the product structure of this here. But as you see, none of this is in general associative. So this seems difficult. But in actual cases, this is very simple sometimes, because this is always non-associative. But in many cases, this is associative. If this is associative, then this can be replaced. The product can be replaced by some very simple product. Let's see the applications. The normal, for example, we have several different products on this total cohomology group. This group, we have the universal product that is not associative, but the normal is associative because we require this to be 0 except it satisfies this equation, so this condition. And such a product is called normal product. And special product requires to be the disjoint union. Here, this means disjoint union. And only this is the usual what we define. Other restriction product are 0. These two algebras are the same group, the same total cohomology group, but with different product. And in many cases, for example, if we give this condition, this is quite a general condition, that co-kernel is an ideal of this, and image are subalgebras of both of these algebras. This in many cases naturally satisfy, and this is naturally associative algebra. And this product may be replaced by the normal, and especially when this suspension, everything is a suspension, this is by the special product. So in many actual cases, this is the computation is not so not very difficult. And here I just want to let's see the final result is that, for example, if everything is this homomorphism is an epimorphism, then we can replace by this is even simpler, the left universal algebra. And especially when this equals this is the Stanley-Reisman ring. And if everything is a monomorphism, then we have this. This is, in fact, the right cohomology. And we have I don't want to talk about the detail because a lot of applications, in most cases, the polyhedral product space, we can define it without any difficulty if you know the definition. And so here, I just want to this is, there are also a lot of examples I didn't write here because I think there are too many examples about polyhedral product space. So I give only some general result. What I'm going to talk about is why we can get this algebra diagonal tensor product structure. Let's see, why is it? That is to say, how can we get this group? It's the most important trick of our proof is that with this. How can we first get this structure, diagonal tensor product? How is this obtained? I want to talk about the I just want to say the detail is impossible to say here. I just want to say the most important trick. We always have this permutation, if everything is a SITI are triangle complexes, and we have the tensor product of triangle complexes, and we have a permutation isomorphism. This is an isomorphism. And here S1 is the free module over 1 and SK epsilon k with d epsilon. I'm talking about the dual case. This is a very simple triangle complex. Free module with generated by 1 epsilon k, d epsilon k equals 1. Tk is just the image plus kernel plus co-kernel. It's a trivial ideal. Differential is 0. And we can usually very easily naturally construct a triangle complex approximation triangle complex to this polyhedral product space. Or what I write here is its definition is natural. I don't want to talk about the detail here. It's very naturally constructed to approximate this homology is the polyhedral product space, the homology of the polyhedral product space. And we can define such approximation is a subtriangle complex of it. And when this isomorphism here, we get It's this trick that we get this, because usually we cannot, this group is easy to define, an approximation of the polyhedral product space, but its homology is hard to obtain. You don't know how to get it. But with this isomorphism, this we have, and this is a trivial triangle complex. Its homology is itself, and it's this cohomology is just this part. And the first is the, it is in fact just the simplicial complex with degree uplifted by 1 of this, the augmented simplicial complex with degree uplifted 1. And notice this definition. This has is naturally a subtriangle complex of it. It is just this strip. I think many people can think of this approximation. It's nothing difficult, but its homology is really hard to obtain. Usually you cannot think of how to compute its homology. But with this, it's a subtriangle complex of this. It's an monomorphism. So with this isomorphism, we get this. And from this point of view, this diagonal tensor product structure is very easy to think of. And the product structure is naturally defined. And with this correspondence, we have that seems a little weird construction of the product structure of these two groups. That is what I want to say here. Thank you.